All right, so hello and welcome everybody. My name's Kelly Rembert. I'm here from the Southfield Library this evening, and it's my pleasure to introduce Paul Gross, WDIV meteorologist. And tonight he is here to present us with global warming, but without the politics. So we're going to talk just science and facts tonight.
Well, thanks a bunch, Kelly. It's nice to see you again, and nice to see you guys that are here. And I want to just take care of a couple of housekeeping items first. And first of all, people ask, why am I qualified to talk about this subject? And I mean, obviously I'm a meteorologist, but that doesn't mean I know anything about climate change. Well, I've actually been covering the subject of climate change for 30 years now. Back in the early 1990s, I interviewed my very first climate scientist, and he was a coordinating lead author of the IPCC that writes that big International Global Warming Report. And so I have traveled the world to meet and interview some of the world's foremost climate change researchers. And in fact, one of them, Dr. Kevin Trenberth, is just in the completing stages of writing a book about climate change. And he actually asked me to write a little, one of those little quotes that they'll put on probably the back cover of the book or on the website. And that was a nice honor. So I have maintained close contact with a number of climate researchers. And if I don't know something, I don't go look it up, go Google it. I email these people and I get the straight answer. So that's number one. Number two, as Kelly mentioned, this is going to be a science lesson. This is not going to be anything that has to do with politics. The subject has unfortunately become political, but I'm not speaking to you from any side of the political spectrum. I'm only speaking to you as a scientist. Everything you're going to see tonight is rigorously verified scientific fact. And a lot of the graphics I'm going to show you are really nice high-resolution graphics that are prepared by a group called Climate Central. They're a non-advocacy group that basically it best be described as a climate communications group. They do their own research, and they also take research done by other climate researchers, and they make really nice graphics that we can use on TV, or in the case of this, use it in a nice PowerPoint that I can show you. So you're going to get this subject. You're going to get a lot of information tonight, and I do not expect you to remember all of it. In fact, you'll forget more of it than you'll remember. But the thing is, there are certain points I'm going to make that you will remember. There are certain talking points you will walk away with that you're going to remember, and you'll be able to use those in discussions with people. Last thing, I want to make it clear that I use the terms global warming and climate change interchangeably. Some people have tried to make a political statement out of using one or the other. No, I don't believe that there should be. I mean, you have climate change, you have global warming. To me, basically the terms would be, it's like climate change would be like saying bread, and global warming would be like saying rye bread. So climate change, yes, climate has changed throughout history. Global warming is this specific warming of the Earth's climate. So I actually prefer the term global warming because it is a planetary warming, but I'll slip and use both terms interchangeably, and I don't want you to read anything into that. So with that, I am going to share screen here. Let's see. It says host disabled participant screen sharing. So Kelly, I need you to do something. Maybe you just did it.
All right, it should be over to you now.
Okay, it is. And I just need to, let's see, here it is. Okay, now I want to start my slideshow. Let's see here. Let's see, from the beginning. All right, here we go. All right, we're going to look at science. This is just raw data I'm going to show you. You're going to look at some indicators of the warming, the impacts. I'm going to get into some local stuff, and very briefly just talk about what the future holds in terms of whether we do something or we don't do something about it. So let's first talk about the greenhouse effect. And this has taken on a very negative connotation, but in actuality, without this greenhouse effect, life as we know it wouldn't exist on Earth. Because what happens, excuse me, what happens is energy from the sun passes through our atmosphere, and certain gases in the atmosphere trap that heat. And some of that heat does go back into space. Well, enough of that heat is trapped where our average temperature is about 60 degrees. The whole planet's average temperature is about 60 degrees. If we didn't have this greenhouse effect, the average temperature on our planet would be 0. So we need the greenhouse effect in order to have temperatures such that we can survive. But the problem is that this greenhouse effect is now kind of running away. And we're going to get into that. All right, let's talk about now And I want to move a little box here so I can see my own graphics. All right. Our atmosphere is made up of 99% nitrogen and oxygen. Okay, most of our atmosphere is nitrogen and oxygen, but there are very important greenhouse gases, which are called trace gases because there's just a trace of them. But the thing is, even though there isn't a lot of it, it's enough to make a big difference. And those are water vapor, carbon dioxide, methane, and nitrous oxide. And again, even though they make up a small part of the total composition of our atmosphere, they have a big impact. And the way to understand that would be, let's say you made an omelet and you sprinkled some pepper on it. Think about the volume, how much pepper there is compared to the volume, how much egg you have on that plate. It's almost nothing. You sprinkle pepper on that egg and it's almost nothing compared to the amount of egg that's on the plate. But think about the big difference in taste that you have when you add that pepper. That's how it works with these greenhouse gases. It's not that there's a lot of them up there, it's that there's enough to trap heat, and we are increasing those gases, as you'll see. All right, this is not new science. I mean, take a look at this. Back in the mid-1800s, 1863, John Tyndall actually predicted, or perhaps you might say speculated or computed, whatever. He basically decided that if we doubled the amount of carbon dioxide in the atmosphere, that would warm the Earth's surface. And you know what? That's what has happened. And then in 1895, Svante Arrhenius, another scientist, he got actually specific with his calculations, and he said that the Arctic would warm by 15 degrees Fahrenheit if carbon dioxide doubled or tripled. Now, at that time, carbon dioxide was 295 parts per million. Okay, this is back in 1895. Carbon dioxide was 295 parts per million, and now it's well over 400. All right. A lot of people like to say, yes, the climate has changed in the past. It's changing again. This is all part of some cycle, some repeating pattern. Well, no. You see, the Earth has warmed in the past. The Earth has been very warm in the past, to the point where the ice on the poles were all melted, okay? And we had life and trees and things way up at the high latitudes. And we had the dinosaurs, when they were roaming the Earth, again, the planet was warm. Those dinosaurs were reptiles. So they needed warmth in order to survive. Well, all of those previous warmings, the scientists know what caused them, and what caused them were astronomical changes. Things like the Earth's orbit around the sun, our tilt, the wobble that the planet has as the Earth rotates, okay? So all of the every single one of those previous warmings was caused by something like this, these astronomical changes. The current warming has not been caused by any of this. None of this is happening right now, okay? So how do we know what the temperatures of our planet were hundreds of thousands of years, millions of years ago? Well, there are a number of things. Now, I don't know if you can actually see my cursor, but here in the upper left, okay, these are ice cores. And that's the most important one, because here's what happens. At the poles, you know, it snows like year round, and it snows especially in the winters. And that snow falls on top of the previous year's snow, and that falls on top of the previous year's snow. And it just keeps going. And so you just keep building up the snow. Well, as that happens, the snow, you know, weighs something, and eventually it crushes the lower layers of the snow. It gets crushed into ice. Well, what happens is that little bubbles of air get trapped in that ice. So the scientists drill these massive cores going really deep, and I forget how deep it is. I don't know if it's like a mile down, 2 miles down, whatever. In any event, they drill these very deep cores, and they see the layers, and they can basically count back the number of years that they're looking back into history. So what they do now that they have a timeline, they put a hypodermic needle into those air bubbles, extract that air, and they can actually determine, because they have it, they can determine what the composition of our atmosphere was back all those years ago. And that's important because when the planet is warmer or cooler, there is an isotope of hydrogen called deuterium that rises or falls based upon if the planet's warmer or cooler. So if they measure the ratio of deuterium in those air samples, they know the relative average temperature of our planet. So we have a really good record, as I'll show you in a bit. we have a really good record of temperatures going back way back into history. Now, there are other things that give us a little more detail, things like tree rings and bands and coral shells and sediment cores from the bottom of the ocean. That gives us information about ancient ocean chemistry, things like that. But the bottom line is we have a very robust record. It's called the Paleoclimatic temperature record. We have a very robust record going back very far back into the past. All right, so let's look at some numbers here. So if you look at this, you can see going back 800,000 years, there are lots of ups and downs in terms of carbon dioxide in the atmosphere. But notice, at no time, this goes back 800,000 years, at no point did carbon dioxide in our atmosphere get above 300 parts per million. And you look at where we are now, this right here is the start of the Industrial Revolution. And you can see it's almost exponential. It is exponential. And today we are above 400 parts per million. I think the last I saw was, 414 or 415 parts per million. And there are some studies now that suggest that this is not just the highest level in the past 800,000 years, it's the highest level of carbon dioxide in the last 2 million years. And so this all began with the start of the Industrial Revolution. Industry and transportation and building and things like that, the manufacturing of concrete, all of that adds carbon dioxide to the atmosphere. All right, excuse me. As I mentioned earlier, there are three main greenhouse gases. Water vapor, we're not going to count because water vapor is the most prevalent greenhouse gas up there. And that's not something that humans don't impact the amount of water vapor in the atmosphere. We do indirectly, we'll get into that later. But we have carbon dioxide, methane, and nitrous oxide. This is a very detailed graph going back to the year 1000. So going back 1,000 years, notice how relatively stable those gases were in the atmosphere. If you go from left to right, look at how stable all three of those heat trapping gases were. And then you get to this area that's boxed in orange here, or burnt orange, whatever you want to call it. Notice at the start of the Industrial Revolution, the gases start increasing rather dramatically. So not only do we see this, but scientists have also, they call it typed the isotopes or the types of those gases in the atmosphere. They actually know which ones are man-made and which ones are natural. And so they know that the proximate increase in these greenhouse gases, these heat trapping gases, scientists know that the proximate cause for that increase is human activity. They know that, okay? All right, if you're wondering about the emissions and all these gases and stuff, 82% of our emissions in this country is carbon dioxide, okay? 10% is methane, and methane, don't just look at that and say, oh, well, methane, it's only 10%. Methane is a much more potent greenhouse gas than carbon dioxide, much greater heat trapping ability. So as methane increases in the atmosphere, that is a much bigger impact, even though it's only 10%, that's a much bigger impact than what you think. We also have nitrous oxide, and we also have fluorinated gas, okay? And keep in mind that some of these gases stay in the atmosphere for hundreds to thousands of years. So everything we do today is impacting things hundreds to even thousands of years down the road. Now, if you're wondering where those sources are, where those gases come from, it's kind of, I don't want to say evenly split, but pretty close in terms of transportation, electricity, and industry. Transportation is 29% of these emissions. Electricity is 28%, so electricity generation. And then industry is 22%. And then you can see you have commercial and residential, like building and things like that. And then agriculture. Agriculture is part of the problem, but it's only 9% of it. But it is part of the problem. And so, but most of it is transportation and electricity production, and then also industry. All right, this is, I consider this one of the most important slides in the entire presentation. I know we're not near the end, but I'm going to try and explain this very simply and quickly for you. Let's say a climate scientist develops a climate model to try and predict our future climate. Well, they have to find a way to test the model. So what they do is they take data from, say, 100 years ago, put it into the model, and then they see if the model can predict what we know has happened, say, in the last 60 years. If the model with the old data predicts what's happened, what we know has happened in the past 60 years, then we say, okay, that model has some value in terms of predicting our future climate. So what they did is they took all of the models, okay, and they took they put everything into those models that could possibly change our climate. So human impact, natural impact, everything. They put everything that could possibly affect our climate into the models, okay? And they came up with the green curve here. So this green line, not curve, line, okay? And started this, starts, as you can see, back in the late 1800s. And so this green line is the climate models, what they've predicted with the old data, with everything, natural and human impact increases in greenhouse gases. So that's the green line. Now, the orange line is what has actually happened. And of course, you're going to get some variation from year to year. But from a general sense, if you look, that orange line is pretty close to what the green line has done. Okay. So again, you're going to find some years where there are some differences where the models didn't get it right. But if you kind of step back and say, okay, let's just look at the overall trend, especially in the past 60 years here, you can see how those models, the green and the orange lines here, those models are pretty much in line with each other in terms of the general scenario. Now, this blue line is important. This blue line, what the scientists did is they reran those climate models. But what they did is they took out the human impact. So in other words, they looked at the models and said, okay, models, what would you predict the climate to have been in the past, past number of years if we left out the human impact? And if you leave out the human impact, that's the blue line. So those models actually have predicted that without the human impact, our climate would have actually cooled a bit since 1960. And that clearly has not happened. We know that that hasn't happened. We know that. So this is the smoking gun, okay? This shows you that without the human impact, our climate could not have warmed as incredibly as it has, particularly over the past 60 years, okay? So this is a very, very important slide. All right. A lot of people think that there is a big controversy and argument among scientists, and that there's a lot of disagreement on the fact that the climate is warming and humans are the proximate cause. Well, actually, and I have to update this slide because now a new paper just came out recently. Now over 99% of actively publishing climate scientists, and that's again in peer-reviewed journals. So in other words, these are science papers that appear in science journals. Over 99% now of climate scientists agree that human-caused climate change is happening. And nearly 100% of them say, or I should say nearly 100% of the papers appearing in those journals find that human-caused climate change is happening. So if anybody tries to tell you that, oh, well, there's this scientist that's saying something that is not with the majority, I mean, is somebody citing some scientist, that scientist is disagreeing with virtually all of his or her colleagues. And so the way I like to explain this is, let's say you looked in the mirror in the morning and you saw like a little lesion on your ear. So you went to your dermatologist and your dermatologist said, I think that's a melanoma and I think we need to carve that out right now. We need to remove that. And you said to your doctor, wait, I want to get 99 other opinions. And after I've heard from you and the other 99, I have 100 opinions, then I'll make my decision what I want to do. And so let's say now 98 of those other doctors say, yeah, I think you have melanoma there. We probably, you should probably remove that. And one doctor says, I think there's enough uncertainty. I think there's enough uncertainty that we should wait and see and then make a decision. What would you do? I mean, I know what you would do and I know what I would do. So for some reason, 99% is not a high enough certainty among the scientific community for policymakers in some countries. So I don't know what more the science community can do. I mean, they've done their work. The science is settled on this issue. So you always are going to find a few outlying scientists that disagree, just like back in the 1950s when those medical studies started coming out saying that smoking was, bad for you. There were doctors that were doing commercials on TV saying this cigarette is healthier than this one. There were doctors saying that certain cigarettes were healthier than other ones. I mean, that's where we're at right now. I mean, we basically, anybody who disagrees with this overwhelming consensus here is pretty much far out there. Okay. And so I just wanted to show you this to show you that there is a tremendous agreement among the scientific community. All right, let's get into some indicators. And so let's first talk about global temperatures. And this includes the oceans here. And so this is a nice worldwide map from 2019. And if you look, anything that's pink or red is warmer than average temperatures for that year. And anything that's blue or light blue is something that was cooler than average. So if you look, it's pretty easy to see. And by the way, gray means that we didn't have data. So it's pretty easy to see that virtually the entire planet was warmer than average. Now, there are a couple of spots. We'll come back to this off of Greenland here. We'll come back to that later, that little tiny spot there. And then you notice the central United States actually had a cooler than average year. And I remember here in Detroit, we were, it wasn't a real hot summer that year. I remember it was just kind of an average summer with a couple of spikes in temperature, but it was kind of a fairly typical, not especially blistering hot summer for us. But if you take a look though, this one little area here in the central United States, virtually compared to virtually the rest of the world, the whole rest of the world was warmer than average. Okay. And again, we'll talk, I'm going to talk more about this little dot off of Greenland in a little bit. All right. I need to get an updated slide for this from Climate Central because the 10 hottest years on record have occurred since 2005. And now you can throw last year, 2020, into that as well. Last year, 2020 was also, in the top 5 or top 10. I can't remember. But and the funny thing is that last year was a La Nina year. And I'll talk more about El Nino, La Nina later. But La Nina years are cooler overall for the planet. So even though it was supposed to be a cooler year, we ended up being one of our warmest years on record. And so last year was now our 44th consecutive year that global temperatures were above average. 44 consecutive years of above average temperatures. And if you're wondering when's the last time the planet has had a record cold year, the last time we had a record cold year for the planet was over 100 years ago. Over 100 years ago. All right, here are the El Nino La Nina discussion. Here is the El Nino La Nina discussion. Excuse me. And what we have is a plot of the planet's average temperatures, okay, surface temperatures, okay, going back, you can see here, going back to, I need to put my glasses on, it's a little, to 1980, okay? Now, the red indicate periods where there was an El Nino, which are warmer years for the planet, and the blue indicates a La Nina year. And by the way, El Nino, La Nina, that's just a shift of the warmest surface waters of the Pacific. In an El Nino, they shift eastward. In a La Nina, they shift westward. That affects the jet stream. So again, La Nina years are cooler. El Nino years are warmer. And so you see that you go back in the 80s here, you see wherever there was blue, it was a cooler year. And where it was red, it was warmer. But now let's go closer to the present. These blue years, you see these blue years here on the right? Those La Nina years, those are cooler La Nina years. Those years, which are cooler, are actually warmer than the El Nino years were back in the early 80s. So El Nino and La Nina are very important drivers of our climate. And you can see how the warming of the planet is just basically overwhelming those cycles. Okay, so El Nino, La Nina, very interesting, and how La Nina years are becoming warmer than even the El Nino years used to be. All right, if you're wondering about just how much agreement there is on temperatures in the past, okay, what you're looking at, each line here, and there are 5 of them, each line is from a different climate change research agency, including NASA here in the United States and NOAA. Okay, which also encompasses our National Weather Service. So 5 different international climate research organizations, they did their computation of calculation of what temperatures were going all the way back to the 1880s. And look at how consistent those results are. I mean, 5 different agencies working all independently of each other, and look at how consistent those results are. So there is tremendous agreement tremendous agreement on what has happened thus far. Okay. All right. So let's get back to the oceans, because the warming isn't just where you and I live over the land. The oceans are heating up very rapidly as well. And remember, we were talking about that little cool spot off the southeast coast of Greenland? And you see it right there now. You see it a little better here. And this is the change in sea surface temperature since 1901. Okay. So anything that's red indicates much warmer than it was back in 1901, and anything that's blue, which is really just this area right here. I don't think there's data right here on the left. So I think really it's just this area right here that's cooler than average. The reason that we think that that could be is the melting ice sheet, the melting Greenland ice sheet. So that cold water is flowing into the Atlantic here, the North Atlantic, and that's a cooler water. It's also fresh water, which is different than the normal ocean water, which is salty. Ocean water is a much higher salinity. So the combination of the different temperature and the different salinity of that water that's flowing off the Greenland ice sheet, we're wondering, and there's a lot of research going on right now, we are wondering if that's going to change our Gulf Stream, which flows off, you can almost kind of see it here, but the Gulf Stream flows off the southeast coast of the US across the North Atlantic. And then that keeps England, for example, much milder than we are in our winter. And keep in mind, England, which is way up here. Okay, I'm going to try and move my cursor across right to the left. I don't know if you can see my cursor, but England is well north of where we are here in Southeast Michigan. And yet they are much warmer than we are in the winter because of this Gulf Stream. So if this Gulf Stream breaks down, there could be a dramatic change in weather in parts of Northwest Europe here. And they're watching that very carefully. A lot of research going on about that. All right. We are very lucky that our planet is roughly 3/4 ocean water, because the oceans are absorbing, if you will, 93% of the excess heat. The rest of the planet, air, land, and water, is only basically warming with 7% of that excessive heat. Let's say our planet was 50-50 land and ocean, then our land temperatures where you and I live would be warming up much, much faster than they have already. Okay. So those oceans are getting warmer, and that's affecting ocean species. And by the way, don't forget this, the oceans are also absorbing carbon dioxide. The increase in carbon dioxide in the atmosphere, the oceans are absorbing that carbon dioxide, and that makes the oceans more acidic. If you like shellfish, think about it. The shell on those organisms is a base. And when you add an acid to a base, they neutralize. And so there could be a significant impact. If the oceans start getting significantly more acidic, there could be a significant impact on a number of different species, but shellfish could be seriously impacted. All right, let's talk about sea level rise. This is something very tangible that people can understand. And this is, each bar here is a century. So you have the 1st century, 2nd century, 3rd century, 4th, 5th, and to the right, this is the 20th century on the far right. So you can see sea levels have indeed fluctuated over the past 2,000 years. But then you get to the 20th century and look at what sea levels have done. We haven't seen anything like that in 2,000 years. Fastest that we're seeing sea levels rise. And I want to tell you something here. This is a great talking point. If you ever hear somebody say that the North Pole ice is melting, so sea levels are going to rise and flood all of our coasts, that is incorrect. Okay. The ice at the North Pole is already in the ocean. So think about it this way. You have a glass of ice water filled right up to the top, right up to the brim. It's a glass of water with ice in it. And you put it on the counter. When the ice melts, does the water then go and flow over the cup and spill all over the table? No. No, it doesn't, because the ice has already taken up its volume in the glass. So when the ice melts, it's basically, its volume is being replaced by water. Okay. So that's number one. The fact that the North Pole ice is already in the water. So when the North Pole, if that ice melts, that doesn't affect sea level. But the Greenland ice sheet and the ice sheet on Antarctica are on land. And as that ice melts, it's now flowing into the oceans, and that's additional water going into the oceans. But you know what? That's only 66%, or roughly, it's roughly 2/3 of sea level rise. Roughly 2/3 of sea level rise is from the Greenland and Antarctica ice sheets flowing into the ocean. This is going to surprise you. You know what 1/3 of our sea level rise is? It's just from the fact that the water is warming. Water is a very interesting substance. When water warms, it expands. That's called thermal expansion. So just the fact that the oceans are warming is causing some of the sea level rise, because the ocean water is just getting greater volume. It's expanding. So sea level rise, let me tell you, I'll tell you right now, if you live on a coast, like in here, let's talk about Miami. I have a friend who's a TV meteorologist, two friends that are TV meteorologists in Miami. So over the years, when they have tides, you know, they have high tide, low tide, they always talk about it. And the tides have never really been a problem. But now with the ocean water rising because of everything I just explained, the highest tides, they call it king tide. That's when there's a full moon or a new moon, that the tides are just higher. Well, when there's a king tide, those now are just routinely now just flooding certain streets certain roads are just flooding now when there's a king tide, because the sea levels are higher. Think about a hurricane coming in with the storm surge, that wind that's blowing ashore. If you're working with a higher sea level, that means that water can be pushed farther inland, in areas that never used to inundate are now getting inundated by hurricanes. All right, this is interesting. Okay, I want to stop this. I got to explain this first. It always just goes when I click to it. All right, this is a really interesting animation, okay? And what you're looking at here is North Pole ice. And the white that you see, that's the oldest ice, okay? The lighter the color, the lighter the white gets to the point where it's blue, that is newer ice. That's important because older ice melts slower than newer ice, okay? So now let me show you what the change has been. Whoa, I didn't mean to do that. Sorry. All right, let's do that. All right, so look at the change. Okay, now we're in 2006, 2007. Look at this. Look what's happening to our North Pole ice. A lot less. I wonder if I can do this and pop back to the first frame. Look at all of that white, all of that old ice, not to mention the amount of ice, and now look at it. So we are significantly denting that North Pole ice, and there's a feedback now that occurs. Ice is, as you know, the ice is with the snow on top of it, the ice is white, okay? And that reflects solar radiation. When you replace the ice with ocean water, the ocean water is darker. And that darker ocean water absorbs more solar radiation than what the ice used to, because the ice reflected a lot of that. So that just further exacerbates the warming at the poles. And so as you then really significantly warm those polar waters, we've had some summers now where the Northwest Passage here has been completely ice-free, and you could actually, freighter traffic could go through there. And so some of the earliest predictions about global warming were that the poles were going to warm the most. And that is absolutely what has happened. The higher latitudes up here, they have been warming much, much faster than the rest of the world. All right, let's talk about something local, the Great Lakes. This graph is very simple. Each year to year, it's okay, what you have is each dot on the line is that year's peak ice cover by percent. In other words, 60% of the Great Lakes were ice covered, or 50% or 40% or whatever. And so, yes, you're going to get big ups and downs from year to year. But the overall trend from the early 70s to the mid 2010s, the overall trend is less Great Lakes ice cover. And when you have less ice cover, that means you have an increase in clouds and lake effect snow in the winter. So we are seeing a decrease in the percentage of peak ice cover in the winter on our Great Lakes. And as I mentioned, lake effect snow is increased when you have less ice. And so you can see here on the graph that since 1980? I put my glasses on. 1930, I'm sorry, 1930. 3 looks like an 8 when you don't have your reading glasses on. So since 1930, you can see, again, lots of year-to-year fluctuation. We're not trying to, tell you that there's not year-to-year changes, but the overall trend over time is for more lake effect snow as a result of less ice. All right, this is interesting. You're looking at Muir Glacier in Alaska. The photo on the left and the photo on the right were taken from the exact same vantage point. The photo on the left in 1941 shows you that glacier. The photo on the right, which was taken in 2004, shows that the glacier has retreated by 7 miles and the thickness of the glacier has decreased by 1/2 mile. That doesn't just happen because you had a warm year or two. This is the result of a systemic long-term warming trend. It's dramatic. This photo is incredible. All right, now I got to stop this. I got to explain it before I see. Now I've learned my lesson. All right, let's look at the ratio of warm, extreme, in other words, record heat versus record cold. So let's say the climate was absolutely stable. It wasn't moving at all. The climate was perfectly stable. You would have, in this white area, this would be kind of your normal weather. And then you'd have an equal amount of this red, which is extreme heat, and this blue, which is extreme cold. So in other words, you'd have equal chances of extreme heat or extreme cold. So now let me show you what has happened as the planet has warmed. You're now going to be looking at the change in the ratio of record heat to record cold. So what you're going to see, so you're starting here, and you're going to start to see a little shift to the right, and look what's happening. So what you are seeing is that, remember at the beginning, remember this white area here right up the middle that was kind of considered normal weather? Okay, well, notice these reds are now well within that curve. You are seeing a lot more record heat, okay? And you can also see, I kind of misspoke earlier. It's not that this left area of the red has not moved into the gray. What I was trying to say is that it's increased in frequency, and you can see that even as you get to the extremes to the right, those have increased in frequency as well. And notice the blue here, that has decreased in frequency. So I'm going to kind of pop from the beginning to the end there. So that would be considered perfectly stable climate. This is what has happened in terms of the frequency of record heat to record cold. And as you can see, this doesn't mean that there's no record cold. Remember the polar vortex winter of 2013, 2014? This doesn't, the rest of the, by the way, that winter, the rest of the winter, the rest of the world was cold. I was warm. We were cold. We were bitter cold in the eastern third of the United States. The rest of the world was baking. I had friends, TV meteorologists in Europe. They were texting me all the time saying, oh yeah, it's like 50 degrees here. And what is it where you are? Oh yeah, it's like 10 below zero. I mean, we were in this bitter cold pattern, but the rest of the world was warm. So again, you still get some extreme cold in a warmer planet. It's just that you get a lot more of the extreme heat. All right. Just in case you're interested, you've seen in the news a lot lately, the fire risk out west. And what you have here, the line here that you see, this up and down like lined, and then this bolder white line here, that's the increase, showing you the increase in temperatures out west from 1980 to 2019. So you've had an increase in temperatures. And if you look at these orange bars, yes, there's year-to-year fluctuation. But these orange bars show that wildfires out west have increased in number as the temperature has increased. And as the temperature increases, usually that's associated with drought too. And you know that there's been incredible drought out there. So this is having a great impact on the western wildfires. All right, let's get into some impacts here. Extreme precipitation. We're talking about the most extreme precipitation events. The extreme extremes is how Chuck Gatica used to like to call it. And every part of the country is seeing an increase in the heaviest precipitation events. But notice the Northeast and the Midwest here are probably the two, not probably, they are the two areas that are seeing the highest increase in extreme precipitation events. Of course, you're going to see big regional variation. But again, these are the top 1% of extreme precipitation events. And so just look at this past summer. I mean, look at the sheer number of incredible flooding events that we had here in Southeast Michigan. That's just Yeah, you can see it reflected in these statistics here. Tornado outbreaks. This is very, very interesting. Okay, so, and I got to explain this here. What you're looking at, the yellow line, which goes up and down, you know, from 1950 to 2017, this is the number of tornadoes that have occurred in the largest tornado outbreaks each year. Okay, so it's the number of tornadoes in the largest outbreaks. So what a lot of the research is showing is that there may be fewer tornado outbreaks, but the outbreaks that do occur may tend to have more tornadoes. And what's also disturbing is that, first of all, the November to February tornado frequency, especially down south, is increasing, as is nighttime tornadoes. And listen, just since the year 2000, we've had 2 big tornado outbreaks here in Southeast Michigan, and I think both of them occurred at night. And that's important because nighttime tornadoes have more fatalities than daytime tornadoes. So I'll let you decide if it's good news or bad news. Fewer tornado outbreaks, but bigger tornado outbreaks. So fewer but bigger tornado outbreaks. Is that good news or bad news? I'll leave you to decide that. All right, raise your hand if you have allergies. A lot of people have allergies, and the news is really not good because with the warming of the climate, we have a longer growing season. And in fact, here in Detroit, our growing season, just since 1970, our growing season is nearly a month longer. And if you have allergies, you know that that means that's an extra month that pollinating plants can be growing and producing pollen. So the last freeze is happening earlier in the spring, and the first freeze is coming later in the fall. That gives us a longer allergy season. But wait, there's more. The carbon dioxide in the atmosphere is changing pollen-producing plants. They are producing more pollen now. So you can see in the graph here, by the year 2085, we're going to have about 3 times more pollen being produced by pollen-producing plants than they are today. So the upshot of this is that allergy sufferers are looking at a future with a longer and more intense allergy season. And then this is one of those talking points, you know, longer, more intense allergy seasons. If you have allergies or you know anybody who has allergies, and I certainly know people that have allergies, this is just really, really bad news. All right, we're getting close to wrapping this up here, and then we'll take some questions. I'm just checking the time here. All right, so this is what this is it's a map. Okay, the white line here is Detroit's average temperature, okay, through the year. So as you expect, here in the summer, this line, this orange, well, I guess, what do you call it? Orange, I guess orange bar here. That's summer, and you can see that our warmest temperatures occur in the summer, and then you can see down here on the far left, our coldest temperatures occur in the winter. So that white line is our average temperature, daily temperature through the year. The yellow line would be our projected, or is our projected average temperature by the year 2100 if significant cuts in emissions are made. Okay, and you can see it's warmer than what our current average temperature is. And if things kind of remain as they are, then we get into this dark orange line here. And look at this. If things were to if nothing were to be done, we were just kind of continue business as usual right now with emissions, by the year 2100, a lot of climate scientists would agree that here in Detroit, we would have average highs well into the 90s by the year 2100 in the middle of the summer. So even just meaningful cuts, not cold turkey and just eliminating. I mean, I think that's just not practical to just eliminate, emissions. You can't do that. But even just meaningful cuts can slow the warming. And I want to tell you something. You all know now what flattening the curve means because of COVID. You've heard that in the news. You heard it all last year. We need to flatten the curve. As I'll tell you, I've been lecturing about climate change for, I don't know, more than 20 years. And basically what I've been telling people is we can't stop the warming at this point. We can't stop it, but we can slow it down. And slowing it down is the same thing as flattening the curve. I've been telling people, without using the term flattening the curve, I've been telling people for 20 years that we need to flatten the curve. We need to slow the warming because that not only gives species time to migrate or adapt, but it gives humans time to mitigate. So we need to slow the warming, and that's doable. But I will just tell you that if emissions are left unchecked, and this was personally told to me by a climate scientist who specializes in regional climate change. He said that a Southeast Michigan summer in 75 years, or close to the year 2100, is going to feel like a Southwest Missouri summer feels like today. So he said by the year 2100, a Southeast Michigan summer will feel like a Southwest Missouri summer feels like today. All right, this is my own research that I did. So first of all, on any given day, you can set 3 different kinds of record heat or record cold. You can set so let's talk about highs. You can set a record for the highest high temperature of the day, so a record high. You can set a record for the warmest low temperature for the day, and you can set a record for the warmest average temperature of the day. So in one day, you can actually set 3 different record warmth or record cold. So what I did is I went back through all the records and I counted the number of record heat versus record cold for the decade of the 1990s. Okay. And as you can see here, we had a 3-to-1 ratio of record heat to record cold. Now, if our climate wasn't warming and it was kind of close to being stable, it'd be not exactly 1-to-1, but it would be closer to 1-to-1. But a 3-to-1 ratio is already showing that something's happening. In the 2000s, from 2000 to 2009, we had a 6-to-1 ratio of record heat to record cold. And then here's the last decade, 133 records that were warm records, 38 cold records. And what's most notable about this is that I believe most of these, not all of them, but I believe like 24 or 25 of these cold records occurred in that one polar vortex winter of 2013, 2014. So you take away that one extreme winter and this ratio is through the roof. So you can see this is a direct local impact. You can see how that ratio of record warmth to record cold is changing. And this one will surprise you. As the world warms, we evaporate more ocean water into the atmosphere. And that atmospheric humidity, that additional moisture in the atmosphere, that is what storms turn into precipitation. Now, we already talked about those extreme precipitation events and the flooding. Well, how about snowfall here in Detroit? Well, look at this. In a warmer world, 6 of Detroit's top 15 all-time snowiest winters have occurred since the year 2002. So in other words, in the past 19 years, we have had 6 of our top 15 all-time snowiest winters. So if the storm track is right or wrong, depending upon your point of view, in any given winter, those storms are dropping more snow. So again, if that storm track is to our south and we're on the cold side, that's why. And listen, we just had in 2015, Super Bowl Sunday snowstorm. What did we have? 15 inches of snow. That's one of our top 2 or 3 snowfalls in recorded Detroit weather history. So that's another physical local impact of this warming. All right, we're getting real close to the end here. You can just see hot summer days. In other words, this is just a count of the number of days in the summer that we had that was above average or above normal for temperatures. And you can see that hotter than average days are increasing. So since 1970, we're averaging nearly 18 more above average temperature days every summer. So you can just see, if you don't like summer heat, this is not something that's good news for you. I don't mind summer heat, but then I was blessed that I can afford air conditioning. So if I need to escape the heat at night to sleep, I can. There are a lot of people that can't, and this is a problem for them. And if you're wondering, by the way, if you're wondering what season is warming the fastest, believe it or not, winter is actually the fastest warming season, followed by fall, and then you can see you have spring and then summer. I mean, all 4 seasons are warming, but winter appears to be the fastest warming season for us here in Michigan. All right, last couple of slides here. So here we are. Okay, we're just before this. This is the 2025 to 2030, where we are projected to cross that threshold of warmth where even more significant impacts are going to be felt around the planet. And so you have 2 different paths here. The current path is where temperatures go. that kind of orangish reddish line. And then with extreme emission cuts, notice that things still warm for a while for the next couple of decades, and then they kind of level off. Okay. And then maybe there, I don't know if there's a slight decrease toward the year 2100, but we can at least level things off with extreme emissions cuts. We're not going to have extreme emissions cuts. I mean, there are people that are trying, but it's just not practical. And unless some magical technology comes out where we can generate electricity without greenhouse gas emissions, I mean, we have nuclear power, but that's all regulatory problems. And so unless something else is able to be developed, we're going to probably be somewhere in between these paths, and we're going to keep warming, and we are going to have some very significant repercussions. And I will just say that back when Detroit sealed a new time capsule back in the year 2000 to be opened in the year 2100, I was privileged to be able to put a letter in that time capsule. And I wrote a letter about climate change. And I told the people, I said, it's hard to write a letter to somebody who's going to read it in 100 years, and I explained what was going on with what we knew at that time about climate change. And I explained, what was going on in the Congress. I didn't get political, but I explained what the political reasoning was for either believing or not believing in what was happening. And then I said, I pray that the warming that we are experiencing is determined to be something, cyclical or repeating, because this letter will be of diminished importance, but that will mean that we won't have nearly the catastrophic future that we could have. But then I said, but if this warming is going to continue as we expect it to right now, if nothing is done, I said, I pray that 100 years from now, you're not asking the question, why didn't you do something 100 years ago when you knew what was going to happen and you had the opportunity to do something about it? And again, you look by the year 2100, I mean, the question they could be asking, one of the things they could be experiencing. Right now, we average 13 90-degree days every year. By the year 2100, we could experience, look at that, nearly 70 90-degree days in a typical summer. I mean, that could happen if we continue on the current path. And this is not just out of the realm of possibility. This is something that's very possible if nothing's done. And by the way, fewer nights below freezing. Present day, we have 118 days where we have a below freezing temperature during the year. By the year 2100, that drops by more than half. And you're thinking, oh, that's good news. No, that's not good news, because there are a lot of pests, things like ticks and other things that are killed by the occasional Arctic blasts that we get. And if you don't get Arctic blasts, you don't get those freezing temperatures, those pests, more of them survive the winter, and then there are more of them in the summer that become a problem for us. So you're looking at this, you're saying, oh, well, that's good news. Well, no, it's not. We need some of this freezing and really super cold winter cold. We need some of that occasionally just to try and knock down some of those pests. So last slide here. Basically, as I said, carbon dioxide remains in the atmosphere for hundreds to thousands of years, and that's going to lock us into some impacts that we've already talked about. And so, again, I don't get political here. I mean, the question becomes, does the world come together as a single world and say, we humans have actually changed the composition of our planet's atmosphere? We have actually changed the composition of our planet's atmosphere. It's hard for people to kind of fathom that, but we have. And so the question becomes, since we have made that change to our atmosphere and we are now kind of suffering the consequences, what can we do about it? And that's for the policymakers to decide. But as scientists, we've explained what's going to happen. We have explained what's happening and what's going to happen. Now it's up to the policymakers. So with that, let's see, I will stop sharing the screen. And if there are any questions, I think, Kelly, you're going to have people put them in the chat maybe?
You can, people can put them in the chat, or you can unmute yourself and ask. We have just a few minutes for questions.
Yeah, that works too. If anybody has a question, happy to answer it. If you want to just ask it personally, that works fine.
Well, I'll ask you one, Paul. So sure. With all of this, first off, thank you. I know I've learned a lot tonight, and I hope everyone else has. What do you say that, without getting political, I'm not trying to turn this into what the title isn't, what can we do though to help?
It's actually, there are a lot of very simple things people can do. And what the great thing is, Kelly, is that these things actually will save you money. And you'll save money doing this stuff. So for example, if you are leaving a room for 20 minutes, a couple of hours, whatever, turn off the light. Don't use electricity that you don't need. So, things like that, things like dialing up in the winter or in the summer with the air conditioning, dial up your thermostat a degree or two. You probably won't even notice the temperature change in the house, but you're going to save energy. In the winter, dial it down a couple of degrees. And what I did, get a programmable thermostat. We have ours set to go down to 65 degrees at night after like 11 o'clock. And you're supposed to sleep in a cooler room anyway. They say it's healthier, but so it stays at 65 overnight. Then in the morning, it comes up and, for when we wake up, so it warms up the house a bit. And so things like that. I have replaced most of the regular light bulbs in my house with those LED bulbs. Now, the LED bulbs are more expensive, but over the lifetime of the bulb, they will save you a load of money. What you'll save in energy costs, those light bulbs, they use, I think, only a quarter of the electricity that a regular light bulb uses. So there's that. There's here's another one. Don't leave anything with a charger plugged into the wall if you're not charging it, you're not using it. So for example, everybody has a cell phone charger. Everybody plugs in their cell phone and their iPad and stuff. If you leave that charger plugged in the wall, even when you unplug your phone and unplug the iPad, the charger is still using a tiny bit of electricity. Now, it's not a lot, but multiply that by, say, 50 million people. Well, now it's a meaningful amount of electricity. So unplug those chargers when you're not charging your phone, you're not charging your iPad. Your hair dryer has that block on the end that you plug into the wall. That uses electricity. If you leave your hair dryer or your curling iron plugged into the wall, unplug those when you're not using them. So those are all things also that avoid putting emissions in the atmosphere. So, for example, drive more efficiently, drive more fuel efficient car. I mean, I have a Chevy Bolt right now. Yes, I know I've got the battery recall I'm dealing with, but they're getting that figured out. But I haven't stopped at the gas station. I haven't burned a gallon of gas personally. I mean, my wife has a gas car, but I've not burned a gallon of gas since I bought the car like 2 years ago. So, I mean, it's a great feeling driving my neighborhood, knowing I'm not putting anything into the air that people can't breathe because it's just running on a battery. So long answer, but lots of simple things that people can do. I think something popped into the chat.
Yep. And it's from Kathleen McNillis. And she says, thanks so much for this important information. And you touched on this already, Paul, but she asks, what are you doing to make a more positive impact on the climate?
Well, I've done exactly everything that I've talked about. The LED bulbs, programmable thermostat, driving the electric car, and there are other little things. Like, for example, on a sunny day in the winter, I will open the blinds, not the windows, just the blinds on the sun side of the house to let the sun shine in, because that actually gives you some heating. That sun, have you ever seen your dog or cat like sleep where the sun's coming in the window? They go to sleep on the carpet there in the sun in the winter. I mean, it does help warm your place. And then as soon as the sun's not shining in that window, close those blinds to help be a buffer between the colder window. And so you'll see less heat translate. So I close all the blinds at night. And then during the day, when I'm expecting sunshine, I open those blinds on the sun side of the house where the sun will come in, and I let that sun come in and help warm the house, which means that the furnace doesn't have to work as hard. So anything that reduces your electricity usage is a real plus.
Well, Paul, thank you so much. A round of applause to you. And I want to thank you both personally and, for working. I've worked with Paul for years on Weatherfest, which is a program hopefully we'll be able to bring back, fingers crossed. But I thank you so much for doing this tonight on our behalf. I
enjoyed it very, very much, Kelly. I'm glad we had the opportunity. And again, you recorded this, so I'm glad it'll be on the website for other people to experience and to basically view at their when it's convenient for them.
Yep. Thank you so much, Paul.
All righty. Thanks, Kelly.